All right. Yeah, so let's graph the sine curve and let's talk a little bit about, after that, we'll talk about what the general equation for a sinusoidal looks like and the way that the variables in that general equation affect the sine, like the transformations that that the mother function would have to go undergo in order to meet this whatever this new equation is. So let's first start with graphing out the sine curve, and the easiest way to do that is since we've already completed our unit circle, we're just going to grab points from the unit circle and plot them onto our graph. So in particular, what I mean by that is remember that on the unit circle, sine of theta, or we're going to kind of start talking about it as sine of x, they're really the exact same thing, but just the context kind of makes a difference. In general, when we're talking about sine of theta, we're talking about like theta represents an angle measure. When we talk about sine of x, we're allowing x to be any real number. And again, there is a one-to-one correspondence between the angle measures and the real numbers, but it's maybe just a slight nuance in terms of how sine of theta, which is on the unit circle, gets translated into sine of x on the xy plane. So remember, sine of theta always refers to the y coordinate. So for instance, the sine of 30 degrees or the sine of pi over 6 is 1/2. The sine of 240 degrees or 4 pi over 3 is negative root 3 over 2. So we're just essentially going to map out or graph out all of these y coordinates. One important thing to note, though, is that when we are translating this over to the Cartesian plane, we're going to be using radians because the radians are what translate over. So for instance, like I have my graph marked off here by pi units, essentially, I guess pi over 2 units. But the point that I'm trying to make is that if we talk about the sine of, say, just pick whatever number you like, sine of 3, that means the sine of 3 radians, not the sine of 3 degrees. So yeah, on our xy plane, we're treating the x-axis as essentially like the input in terms of radians. All right, so let's just start graphing some of this. The easiest one, sine of 0. So when theta is 0, or when x is 0, the sine of 0 is 0. So sine of 0 is 0. Sine of x goes right through the origin like that. Let's see here. Well, I'll just go with all of the points first that I've listed on the positive side of this x-axis. So the next easy one would be pi, and boy oh boy, this is going to be not anything interesting. The sine of pi is 0. All right. So far, it looks like a very strange equation, or a very strange graph. And then the sine of 2 pi, well, 2 pi is the same, 2 pi radians is the same, is equivalent. It's not the same, it's equivalent to 0 radians. So sine of 2 pi is equal to the sine of 0 is 0. Okay, now let's mark off the pi over 2 units. So let's see here. Here's pi over 2. At pi over 2, sine is 1. So up here, we'll go through this point about right here. Yep, that's it. And then sine of 3 pi over 2, well, sine of 3 pi over 2 is negative 1. So at 3 pi over 2, we're down here at negative 1. And the graph is starting to form. You can see it's a wave. But we'll put in just a couple more pieces in here just to kind of get a few more points on this wave to really satisfy ourselves that it does end up looking like that sort of curvy wave. So what else do we have to work with? Well, since I've listed this out by pi over 2 units, the next easiest ones to capture would be the multiples of pi over 4. So sine of pi over 4 is root 2 over 2. Root 2 is like 1.414, so half of that is about 0.7 something or another. So, and pi over 4 would be right here in between these. 0.7 here would be about 0.5. 0.7 is maybe up here. Yeah, about right there. And it'll be the exact same thing over here at 3 pi over 4. So at 3 pi over 4, sine of 3 pi over 4, again, root 2 over 2. So it's about 0.7. 3 pi over 4 is about right here. It's nice and symmetrical, like that. I have a stray mark that is bugging me. Okay. Let's see, sine of 5 pi over 4 is negative root 2 over 2. So about negative 0.7. So maybe here. And then sine of 7 pi over 4, also negative 0.7. So right there. We could also put in the sine of, 30 degrees and the sine of 60 degrees, so 1/2 and root 3 over 2. But I think that what we have right here is really enough. That might be a little bit of overkill to keep graphing that, because the form is emerging. And it's something like this. I'll do it the best that I can. See how well I scaled all of this and drew all of it. Part of the reason that I like math is because I think it's really pretty. So I spend some time trying to make these graphs look pretty. I spend some time trying to make my, when I'm writing things out, I try to make it look pretty. That's a lot of what I find satisfying about math, is just how pretty I think it is. So there's, this is one period of the sine function, and if we were to extend this further out, it's just going to continue because it's periodic. It just circles back on itself. So like right here at 2 pi, now this is equivalent to being here at the beginning again. It's just going to repeat itself because 2 pi is it's equivalent to 0 degrees. So, or 0 radians. So if this was to keep on, it would literally just keep doing this sine. I guess that's not helpful for you if you don't know what the sine looks like. It would just keep doing this wave over and over and over again. Perfectly periodic, every 2 pi. It's just going to make this exact same shape. And so too will it keep making this same shape if we move back in the other direction. So I'm just going to plot out a couple of points to help me maybe draw this somewhat accurately. Keep getting emails apparently. Classic. Nobody emails me when I'm doing nothing. They only email me when I'm making a video. And yeah, negative 2 pi right there. Okie dokie. There we go. So again, this is probably the part where you want to speed up the video, because I'm going to sit here and feel like this is all super important, making it look pretty, and you're probably just like, all right, dude, like, come on. Give me the answers. Just tell me what to do. I don't care about this artistic crap. Yeah. It's alright. It's not perfect. But it's good enough. It's pretty. How's it look? Yeah, it's alright. It's not perfect. I don't know how to make it perfect. It looks alright, though. Okay, so here it is. This is the sine function. The key characteristic for me, because if you're in trig right now, there are 6 different graphs you're going to need to familiarize yourself with: sine, cosine, tangent, cotangent, cosecant, secant. At least for now, if you're at this point where you're just learning sine, later on we also get to throw in the arc sine, the arc cosine, the arc tangent, and those ones I think are a little bit more complicated. So, okay, this is what the sine curve looks like. Right, and what I was going to say before I kind of went on a tangent is that for me the key characteristic is that the sine function comes up through the axis, just like this. Very similar to the graph of y equals x. And in fact, at small values here clustered around 0, y equals x approximates sine. So that's how I remember what the sine graph looks like. Obviously, it's a wave. It has a period of 2 pi. It comes up through the origin. This is distinct from the cosine, which is actually just a phase shift. If I was to take this whole thing and just move it pi over 2 to the left, so that this piece right here, this peak was right here on the y-axis at 1, that's the cosine function. It just comes down, it does the same wave. So they're just phase shifts of each other. Right, so there is the sine function. And again, you could do the exact same thing with cosine. You can do the same thing, in fact, with tangent, cotangent, cosecant, secant, in order to make out the graph. But for now, I would suggest just really focusing on the sine curve, because it's kind of fundamental, and moreover, because where we want to go with this is we want to be able to take an equation, a sine equation, just like if that's given to us, we want to be able to pick it apart so that we can actually graph the equation. So what does the generic form of sine look like? So this is, by the way, this is, I'll write it as f of x rather than y. F of x equals the sine of x. That's what we graphed. But this is a very specific type. This is like the basic sine function. We can add in variables and transform this, just like you did in college algebra. Remember, we beat that to death in college algebra, as we give you a quadratic, and then we give you like kind of this weird form of the quadratic, and we say, oh, okay, so what transformations does y equals x squared have to undergo in order to make this new equation? Yeah, we're going to do the same thing here, but now it's going to be with, oops, now it's going to be, I ruined my drawing, and now it's going to be with trig functions. So the generic form of sine, and this is going to be the exact same thing for cosine, tangent, cosecant, secant. This is the way that I write it. You'll find it different in different books, but I think that this is the easiest form, at least for me. Maybe it's just because at some point this is how I learned it myself. F of x equals a sine of bx minus c plus d, where a, b, c, and d are just real numbers. And when we manipulate our mother function, sine of x, by adding in some variables, and the variables are here, it's just that they're all ones and zeros at this point. When we change a, b, c, and d, it changes the function itself. So the question is, all right, how does it change the function? Because we want to be able to look at, be given something of this form, and then be able to just kind of graph it out, like without using Desmos or a graphing calculator or whatever else it is that you use. So let's just go through and label some of these. For me, the kind of easiest ones to understand and to see are both A and D, because they operate fairly intuitively, again, in my opinion. So A represents amplitude, which is literally the distance from midline to peak or trough. It's not the distance from a peak to the trough. It's the distance from the midline to the peak or the trough. And what do I mean by midline? I mean, what is the horizontal line that our wave function oscillates about? So a really standard example of what a sine function might represent in sort of a real world application is the swing of a pendulum and the displacement, like its movement relative to time, where it's at relative to time. It comes out to exactly something like this. And the midline of the pendulum is kind of like right where it's hanging straight down, right? It oscillates around that midline. And it's the same thing here. So the mother function of sine oscillates about the x-axis. So it oscillates about the line y equals 0. And that's what the midline is. So the amplitude is the distance from midline to peak or trough. So that distance is a distance of 1. So the distance from midline to peak is 1. The distance from midline to trough is 1. That's what A represents. So changing A changes that. If A was 2, then the distance from midline to peak is now 2. So something like f of x equals 2 sine of x takes this exact same graph and just kind of like stretches it by a factor of 2. So it reaches up to 2 and it goes down to -2. So that's amplitude. D represents vertical shift, just like it did with the parabola. Remember? So if you have like something like x squared plus 2, it takes the graph of x squared and it just shifts it up 2 units. It's the exact same thing here. The vertical shift D just shifts this thing up or down. So if D is, say, 3, take this exact same graph and just shift every point up 3 units. So it's just sort of like a wave that's now hovering. It's oscillating about the line y equals 3. D specifies the midline. So D is the midline. So if D is 3, then the midline is the line y equals 3. Okie dokie. The slightly more complicated ones are B and C. And the way that I have written this is it somewhat muddies the water. I can see how it muddies the water. So I'm going to write this just as an example, but then I'm going to erase it because to me I think it probably will just be more confusing. But some texts write the generic form something like this: A sine, and then they do a square bracket, B, then in parentheses, x minus c plus d. So they like factor out this b, which is the smart thing to do. But to me, I think it's less common that you're going to see equations written this way. B is going to be distributed in. So you might have something like f of x equals, say, 3 times the sine of 2x minus pi. That's how it will be written. And so in this case, like, yeah, this is the smart move because it really separates like what's going on the inside, what B and C do. But more commonly, you're going to see equations written this way, and you're going to have to separate those pieces yourself. All right, so let me erase all that because that's not the form that I want to play with. I want to play with bx minus c like this. So B, what does B have to do? B affects the period, and it directly affects the period. In particular, it affects it using the identity that the period is equal to 2 pi over b. Technically, it should be the absolute value of b. Why do they do that? Just because period is sort of a measure of time. So if b is negative, which is allowed, b is allowed to be negative. But if you plug b directly into period equals 2 pi over b, then all of a sudden your period is negative, which just from an intuitive standpoint doesn't really make a lot of sense. It's just kind of like a customary thing. So in any case, period is equal to 2 pi over b. C, what does C do? It affects, again, it isn't exactly, but it affects the phase shift. Phase, or the horizontal shift. So phase shift is kind of used, at least as I've seen it, it's used fairly exclusively with sinusoidal functions, wave functions. When you're working with just like polynomials, like x squared, we usually call it the horizontal shift. It's the exact same thing. The phase shift is just the horizontal shift, how it moves left or right. But B and C, well, B in particular, B kind of affects, while it affects the period, you can think of, like, in terms of what it does with the graph, it's either going to compress it or it's going to stretch it. Think of like an accordion. If I could grab these endpoints and push them a little bit further together, then the wave just moves a little bit faster. If I can pull them apart, the wave moves a little bit slower, which is really just affecting the period. C affects the phase shift, the horizontal shift. But you've got to be careful. The way that I've written this in particular, C does not directly give you the phase shift. The phase shift is given by, in fact, C over B. And that's the reason that some textbooks do like to factor out the B, is that then phase shift doesn't have to do anything with B, it does just have to do with C. But again, I think that maybe can be a little bit confusing, personally, for me. Maybe not for you. It's okay. But the phase shift is directly given by C over B. And in particular, it is a shift right if C over B is greater than 0. It is a shift left if C over B is less than 0. And this right here, I think, is fairly intuitive. This kind of follows our intuition that if the piece, the variables that have to do with the phase shift, if they're positive, that means it's shifting everything to the right. If they're negative, it's shifting them to the left. The confusion, though, is notice that the generic form is given with a negative in here. So if you had something, for instance, back to like sine of 2x minus pi, something like that, you might look at this, you might see the negative right there, and you might think, aha, well, less than 0, that means a shift to the left. But no, this negative is part of the general form. So this 2x minus pi is actually a shift to the right. And in particular, the other really common mistake that people make, again, this is why I like to teach it this way. The really common mistake that people make, they might catch that. They might say, okay, this is still a minus, so this is a shift to the right. And then you might ask, well, how much of a shift is it? How many units? And they might say, pi units. No, it's not. C over B gives you the phase shift. So yeah, and this is the place where rather than writing this for the generic form, you might want to just kind of write this on your own when you are analyzing these things. Now factor out the 2. And when you factor out the 2, you have to divide both 2x and pi by 2. So this would become 2 times x minus pi over 2. And yeah, this piece will give you directly tell you what the phase shift is. This is a phase shift to the right of pi over 2 units. And this 2 would compress everything together. It makes, you can think of it as making everything move twice as fast. So this 2 would change the period from 2 pi to 1 pi. So this thing would just like, everything gets compressed a little bit, like scrunched together. So that is sort of the overview of these functions. And again, I'm just doing this for sine, but everything that I wrote right here, maybe not up here, but everything that I wrote right here applies to cosine, to tangent, to cotangent, to cosecant, to secant. It's all the exact same thing. So what is the generic form of, say, tangent? It's f of x equals a tangent bx minus c plus d. The thing that does change, actually, I guess now that I've said that it's the exact same thing, there is actually one thing that changes, which only changes with tangent and cotangent, which is this line right here. Yes, with tangent, b still affects the period, but the period of tangent is not 2 pi. The period of tangent is pi. So for tangent, b affects the period in the sense that period is equal to pi over b. So I'll just maybe like make a note like that. Period equals pi over b for tangent. And for cotangent too, of course. Whatever applies to tangent is going to apply to cotangent. Whatever applies to the function itself applies to the reciprocal. In general. Maybe I shouldn't say that so concretely because I'm sure that there's nuance. That's the thing. That's the tough thing about math. There's always nuance. That's why math people speak so precisely. We really insist on speaking precisely, and among math people, I'm probably one of the less precise. Yeah. Okay. Let's see, what else do I want to say? What are we at? How long is this? So far it's 24 minutes. Okay, I think that that's good for now because I don't want to make these insanely long, but I do want to make another video where we kind of play around with all of this in practice, but this is the theory of it. If that's all that you need for now, let me know what questions you have.